Hi everyone, I'm Naina Goswami. I'm a MinEx CRC PhD student at ANU, and I will be presenting my work on the argon-argon geochronology on drill core samples from Anabama Hill Cu-Mo prospect in South Australia. This work has been supported by MinEx CRC, which is funded by the Australian Government Cooperative Research Centre program. The motivation to study this granite comes from a variety of sources. The Anabama Hill Granite is a copper moly prospect that has not been extensively explored in the past, which means it has a huge potential for new results and has hidden wealth of information. The outcrops are scarce, and the ones that are exposed are rather distributed. The area is of geological interest as it has been documented to suffer mineralization, alteration, and some degree of deformation. Therefore, this region is captivating for someone like me who wants to explore mineralization and understand subsurface geology of a scarce granite. Let's take you to a tour of this amazing geological unit. Anabama Granite is an early Ordovician granite and is part of the Nakara Arc, which is a tectonic subdomain of the Delamerian fold belt, expressed largely by sediments of the Adelaide geosyncline sequence emplaced into a north-south oriented rifted system during the Neoproterozoic Cambrian period. The Pluton is northeast trending, and it's approximately about 65 kilometers long and 9 kilometers wide, emplaced into the weakly metamorphosed Adelaidean sediments which were deformed during the Delamerian orogenic cycle, forming major geological structures. Now, as mentioned before, this region is a copper moly prospect, and it is of interest. But also, it's interesting because of its similarities with mineralization and alteration styles at Bendigo and Netley Hills. So what is the significance of Anabama Granite? The granite was emplaced during the climax of the Delamerian orogeny, and so it is important to understand the tectonic environment during that time. In general, it is a biotite granite defined by weak foliation, with varying lithologies ranging from granites, granodiorites to adamelites, displaying multi-stage alteration of varying degrees and styles such as potassic, phyllic, propylitic, and argillic, most of which have not been timed very accurately. Along with this, there is prominent sulfide alteration evident consisting of molybdenite, while pyrite and chalcopyrite form the main copper phases. As mentioned before, the granite hasn't been studied extensively in the past, with most researches centered during the 1960s to late 1970s. Therefore, it is crucial to correctly time the ages of emplacement, alteration, mineralization, and any other late-stage tectonic activities. So Anabama Granite is a northeast trending Pluton lying on the eastern margin of the Mount Lofty Ollery Arc. The granite was emplaced into the late Proterozoic Adelaidean sediments, and the emplacement age for this granite is estimated to be somewhere between 470 to 450 million years through various geochronometers. At approximately similar times, igneous activity was widespread near the eastern margin of Adelaide geosyncline encampment to trough, with granite emplacements at Bendigo, Palmer, Victor Harbour, and Kangaroo Island. Two alteration events have been previously timed at Anabama Hill, with Grison event reflected through the potassium-argon muscovite ages of 450 to 455 million years, and a younger thermal event timed through the potassium-argon biotite age range of 432 to 444 million years. Because it is such an interesting area, and most of the Pluton is subsurface as can be seen in this aerial image, diamond drilling was undertaken in the late 1960s, and 7 drilling sites were identified for recovering cores to investigate mineralization and subsurface features of this Pluton, and to also identify targets for exploration purposes through understanding structural controls. The granite has some key features which were yet to be understood, such as the stages of alteration and variety of intrusive phases. A huge amount of work was completed by the exploration companies that document the presence of hydrothermal activity along joint planes and shear zones, with diverse alteration styles identified. Along with this, a question was posed about the source of granitic melt, if it was generated from the melting of the metasediments or was sourced from the mantle. It was also concluded that there was renewed igneous activity after emplacement of the granite, which is potentially the grisonization and alteration events mentioned before. Of course, this granite has a lot to offer. So we decided to undertake argon-argon geochronology on small drill core samples from 7 different drill cores to constrain the timing of crucial events such as emplacement, alteration, mineralization, and intrusion. An argon-argon geochronometer is actually very efficient in doing this. Sample selection is a crucial step as a sample has to be representative of the problem we are trying to address. That is, if timing alteration, the sample has to be a potassic mineral formed in an alteration environment. The data then obtained from the diffusion experiments and ages determined are used to construct a thermal history, and the interpretation is done in context of the region of interest. Microstructure identification is one of the crucial steps in argon geochronology to understand the textural relationship among the minerals in a sample. We observed chloritized biotite indicative of alteration and presence of white-mica. We observed presence of 2 generations of biotites forming a decussate texture. Later stage K-feldspar encapsulating white-mica containing biotite relics and chloritized biotite. K-feldspars displaying pervasive alteration indicating late-stage thermal activity. Cuspate irregular shaped biotites indicative of their consumption during later thermal processes, and king biotite indicative of some degree of deformation. Therefore, argon geochronology was conducted on white-mica, biotite, and K-feldspar from these samples displaying very important ages. So here is an age spectra from biotite. So age spectra is basically a representation of apparent ages as a function of 39 argon released in steps. Each box on the spectrum is a step in the experiment. Biotite shows ages of 459 million years while preserving an older age of 468 million years. Similar younger age is also shown by white-mica of 457 million years. On the contrary, the coexisting K-feldspars preserve younger ages of 371 to 373 million years and an older age of 377 million years. On comprehensive investigation of white-mica spectrum, we observe a classic muscovite subspectrum in the first 3% of gas release that reflect a cooling age of 476 million years, closer to the approximated emplacement age of this granite, while the remainder 90% of gas release has a plateau age of 457 million years. This shows the growth of a later, more retentive domain in white-mica at 457 million years. The conjoint inversion of diffusion data from K-feldspar reveals that 3 different episodes of metasomatic regrowth have occurred, where the K-feldspar regrows at 377 million years, followed by 2 episodes of metasomatic K-feldspar growth at 373 and 371 million years. All of this data, when used to generate a cooling curve following Newtonian cooling, demonstrates an emplacement depth of 5 to 6 kilometers. Therefore, the following inferences can be drawn from this study. There is concrete evidence for metasomatic activity indicated through the progressive stages of alteration observed in the cores displaying variety of alteration styles. The muscovite biotite ages ranging between 458 to 460 million years reflect the age of first hydrothermal alteration event, which is also supported by the unpublished molybdenite rhenium osmium ages of 462 million years, indicating contemporary mineralization and alteration. On examining the muscovite subspectrum, a cooling age of 476 million years is observed, which is closer to the approximated emplacement age for the Anabama Granite. The spectrum also records the growth of a later, younger, more retentive domain in muscovite at 457 million years, from which an emplacement depth of 5 to 6 kilometers has been estimated. The conjoint inversion of K-feldspar diffusion data reveals K-feldspar regrowth at 377 million years and 2 episodes of metasomatic growth at 373 and 371 million years. The ages correlate well with the timing of thermal activities in the lacunar fold bed. Now, this is not all. This is an ongoing study and there is so much more to be done. However, the current results look very promising. Here are the references, and thank you very much.